Probability is something that is hard to understand and to communicate. Different people perceive it differently, and different people have different problems in um, learning the main concepts. In this short demo, I shall use Excel to simulate random numbers from a normal distribution and to use them to show an important result in the calculation of probability and statistics, which is the law of large numbers. So let us at first simulate one random number coming from a normal distribution. A normal distribution is characterized by two parameters: the mean, which I set here to 0, we'll change it later, and the standard deviation, which I will set to 1 right now. I'll make a little bit of room so that things are easier to look at. If we want to sample one normal random variable, we can use the rand function in Excel to first sample one uniform random variable. That means a random variable which is distributed uniformly between 0 and 1. If we press on the F9 button, it will repeat the simulation and convert it via the inverse transform to a normal. So how is this done? There's the function norm s inf, which is the inverse distribution function of a standard normal. So if we have this, we for example observe minus 0.17 plus 0.18 plus 2 plus 0.3 minus 0.21 and so on. Every time we press on F9, we get a new number. Now, how are these numbers that we generate distributed? Are they actually distributed as we would like to, as a normal distribution? That means one of these distributions that has a shape of a bell. To analyze this, we will simulate a great number of them. We will first sample in a row, and I will prepare room for sampling 10 times. Here I will then already make one change which will be useful for the rest. I said here we are sampling a standard normal distribution, one that has 0 mean and 1 standard deviation. We can also sample from a general normal distribution where we actually set the standard deviation to a cell and also use a different mean. Right now they are the same as for a standard normal distribution. In the future we will change them. So we have done that. We can recopy this and we see F9 changes the numbers. Now we can do this entire thing 100 times. I will make a range which have 100 rows. Gotten this wrong here. Do it one more time. 2. I would like to get 100 rows. 90, 100. There we go. And remember, if you select a range adjacent to another one and you would like to fill down the formulas, you can just go in the corner until you get the black cross, double click, and you get it filled down. So now we have 10 times 100, 1000 normal numbers as we think. We should maybe check that they really look normal, and for that we may want to make a histogram. A histogram has several components for construction. One of them is called the bins. So let's create bins and you will see right away in a moment what they mean. We'll go from -10 to plus 10. And what we will do is every time we will ask how many observations are below this number and above the adjacent number. Here we have nothing adjacent, so we only look at the ones that are below or equal 10. An Excel function that does that very nicely is count. If we would like to count the number of random numbers, which I will fix here for later use, and we would like to see whether they're less or equal to what we have here, M4. We use this gluing together operation so that we can then copy down the formula for the other counts. So for the first count, we see that there were 0 observations which were below -10. If we copy this down, we will see that at some point all observations are below. For example, all observations that we simulated here are below 4 in here. Now, if we want to count the number of observations between -9 and -10, we have to do it a little bit differently, because here we count everyone below -9, including the ones that are below -10. So we have to subtract the other ones. So we have count if, and we say minus, and we have to link this to M4 because this is the right place, and we can copy this formula down. We already see that even visually this produces something that resembles a histogram. We can show it even in a nicer way by using a conditional formula. We want to have data bars. We will go into the custom rules and say from right to left, because this is a little bit nicer in this context. And here we have the histogram. Let me make it a bit wider so it's nicer to look at. So this is the histogram of the normal numbers that we have, and indeed this looks like a bell-shaped curve. We can also look whether our arrangement of mean and standard deviation works. Let's at first move the mean. 1, 2, 3. There we go. So this is quite nice. Let's check the standard deviation. This should now get wider. Yes, indeed it does. Looks a little bit asymmetric. Is this something that is just a fact of chance, or is there a problem here? Let's simulate a couple of times. Oh yeah, it's just a fact of chance. There's nothing to be worried about. So this was simply checking whether the random numbers that we generated were actually looking like normal random numbers. Now I'm going to show the law of large numbers. The law of large numbers says that the variability of an average taken over n numbers, the standard error of this average, is equal to the standard deviation of the individual observation divided by the square root of the number of observations. Here we have 10 observations. We can take their average, which I will call mean. This is the average function. The average function we can take here. So every time it calculates an average, there we go. And we can ask ourselves, what is actually the standard deviation? What is the mean of them? If we have an average of individual random numbers, which all came from a distribution with the same mean, we would expect that also their averages will have the same mean. So if we take an average of averages, we expect that we get here we had set a mean of 0, that we will get a mean that is, I will call this grand mean of about 0 again. So here we say average and indeed it is close to 0, sometimes positive, sometimes negative, and we can calculate a standard error, so the standard deviation of this sample of means. And we find 0.6, 0.6, 0.6, 0. And how does this relate to the original standard deviation? Let's calculate the ratio between the two. 2 divided by this. So it's 3.76, 3.1, 2.79, and so on. It's on the order of 3. Yeah, we were saying that the standard error of an average of n numbers has the standard deviation of the individual numbers divided by the square root of the number of observations. The square root of 10 is approximately 3 point something, and this is what we see here. Let's look at the distribution of them. So here we have already all in place to also draw a histogram of the means of 10 observations. Let's do that. So here is the definition of COUNTIF. Let's take the more complete formula and adapt it to what we have at -10 in a moment. So here we have again a copy of it. And so if we just pulled it down, we would get the same numbers again, but we don't want the same numbers, but we want to have a different data area. The data area we would like to have are the means instead of the individual observations. And we have to get them here. And we have to copy them down. And we can draw the histogram that comes out of this. Data bars, as we did before. More rules. Come left to right to left. Let's give it a different color. There we go. And we see that the histogram of the means is a lot more concentrated than the histogram of the original observation. We can simulate this a couple of times to see how stable this result is. Now this shows directly by simulation the law of large numbers, that when we take an average of n observation, the variability in this average, the standard error of this average, is related to the standard deviation of the original data. We should demonstrate this. Let's make this here a little bit larger even, let's say 3. And we will see that also the standard deviation of the means will increase, and that the relationship is according to the individual standard deviation divided by the square root of the number of observations. So here we had in the beginning a standard deviation of 3. We have 10 observations. That means we have to divide by about the square root of 3, which is 10, which is about 3. So we will get a standard error of the mean, which is a little bit smaller than 1. This is what we observe here. This ends the little demonstration about simulating normal random numbers and using these simulations to demonstrate the law of large numbers.